We were looking at logistic regression and when it is used. Typically, when your dependent variable is a categorical variable, we end up using a logistic regression. The categorical variable could have multiple levels, in which case you would use an ordered logit or a multinomial logit. If it has only two possible outcomes as the possible outcomes, then we would use a binary logit. And in this class, we are going to focus on binary logistic regression. We were looking at a bank case study to sort of understand the concepts of logistic and how they apply. We were looking at a bank that had, for a set of customers, had sanctioned personal loans, and they have this historical data where they have tracked the loans and they can see who's defaulted on the loan and who has not. They also have data on some attributes of the customer via the application form, so things like income, employment status, etc. And they want to relate now the default behavior to attributes of the customer with a view of assessing loan eligibility for future customers. So if someone, based on the model that we build, if we take a future customer and we say, okay, this person based on the data on my model is likely to default, their loan eligibility will be low. If they're not likely to default, their loan eligibility will be high. We took a look at the different types of variables that we had. We had categorical variables as well as continuous variables. Income and employment status were categorical, credit score was continuous. Now, one thing we can do just to understand the concept better is to start with a simple model of a logistic. So we'll assume one independent variable, one dependent. So credit score is the independent and the default variable is our dependent variable, which is a categorical variable. Now, one of the first things that I would want to do when building a regression model or looking at a relationship is to essentially look at a scatter plot between my independent variable and the dependent variable. So if I do that for credit score and default, this is what I see. A chart that looks like this, which is maybe not as useful because the default variable can only have 0, 1 values. So this is really not showing a relationship between credit score and default. How could we potentially think, how could we improve this chart, or is there a better way of coming up with a chart that shows us the relationship? One thing that we could try is take the credit score variable and bucket it into different buckets and look at the total number of default versus non-default instances we have in each bucket, or the proportions of default versus non-default that we have in each bucket. So if I'll show it to you in Excel. I take the data that I have, and in my data the credit score ranges from 400 to 900. So I create multiple buckets in increments of 50, and I've chosen 50 arbitrarily just for illustration. So I do 400 to 450, 451 to 500, etc. And what I do is I count the number of times I have non-default behavior and the number of times I have default behavior. In this data set, remember that default is coded as 1, non-default is coded as 0. So the number of zeros I have in each range and the number of ones I have in each range. Now, of course, rather than just looking at absolute numbers, I should be looking at percentages. So if I take a look at the percentage of non-default customers in each bucket, you can see that as the credit score increases, the percentage of non-default is increasing. And this is an intuitive result, right? Higher the credit score, the more likely they're not going to default. If I wanted to visualize this, I would end up with a chart that looks like this. I simply took the percentage of non-default against the buckets, and I end up with a chart like this. Now, notice a couple of things that are interesting about this chart. First of all, there is no linear relationship between percentage of non-default and credit score bucket. The relationship is certainly not linear. In fact, if I join the points together, I'm going to end up with something that looks like this. I'm going to end up with a chart that looks like this. If I join the points together, I'm going to end up with something like this. This is not a linear relationship. In fact, what this is called an S curve. This is called an S curve because of the shape of the curve of that is there on the chart. So what is an S curve? In an S curve, the probability of acceptance is not linear. The probability of non-default, the word that I use here, acceptance, is really if someone is not likely to default, you will accept their loan application. So the likelihood of non-acceptance or of non-default is not linear. We can see that almost no one is defaulting at the higher end, and almost everyone is defaulting at the lower end, right? So almost no one is will be sanctioned a loan at low scores of credit history, and almost everyone will be not defaulting at high scores of credit history. The change in probability of being sanctioned a loan, or the change in probability of non-default behavior at the low end and the high end of the credit score is minimal. In other words, the likelihood of changing the in non-default behavior is very low at the low end and very low at the high end. But in the middle, there is a big change in probability between the defaulting versus non-defaulting. So the likelihood of non-default behavior increases dramatically in the middle of the data. So this is what an S curve really is capturing. Now, another very interesting thing to note about this S curve and that chart is that the percentages of ones in any buckets, which is essentially the percentage of default, for example, is essentially the probability of default in that bucket. In other words, if you take a look at this table here, if I were to ask you that, okay, I have a random bank customer now and their credit score is between 801 and 850, what is the likelihood that they are going to not default on a loan? You will answer 85%, because the likelihood of them not defaulting is 85%. Or if I had to ask you, supposing I have a customer and their credit score is between 501 to 550. What is the likelihood that they are not going to default on the loan? You will say 0%. It's very likely that they are going to default. So really what you have here, this percentage of non-default, is a probability. So on this chart, the y-axis has become probability, right? The percentage of non-default is really the probability of non-default. So what we have now, the equation has become the probability of non-default y is equals to beta 0 plus beta 1 times credit history plus the error term. Credit history is in buckets. Now think about the values of y. If we have y as my response variable, which is the probability of non-default, what sort of values can y take? Y can take only values between 0 and 1, because it is a probability variable. So if I use a linear regression model, one of the problems that I have is that the predicted values that I'm going to get from a linear regression model are not restricted to between 0 and 1. They can be unbounded. So with a linear regression, typically, the output, the predicted values can range anything from minus infinity to plus infinity. So they're not bounded. They're absolutely unbounded. Now I'm going to have a problem with that, because if my dependent variable is a probability, I need the values to be between 0 and 1. They can be continuous values, but they have to be between 0 and 1. They cannot be from minus infinity to plus infinity. So how do I deal with this issue? So what I can do is do something called, and this is where the logistic transformation comes in, take the odds ratio and log that. I'm essentially transforming my dependent variable into something that can take values from minus infinity to plus infinity. What I do is first I calculate an odds ratio. An odds ratio is nothing but the probability of an event by 1 minus probability of that event. And then I take the log of that odds ratio. Why do I do this? The p over 1 minus p, can take values from 0 to infinity. P over 1 minus p can take values from 0 to infinity. If p equals to 0, p over 1 minus p is 0. If p equals to 1, then p over 1 minus 1 is infinity. So, my p is obviously the probability of the event. So first I transform this p variable into p over 1 minus p, then it becomes an odds ratio. Then I take the log of that, because then if I take the log of a quantity that can range from 0 to infinity, then the log of that quantity can take values from minus infinity to plus infinity. So all we are doing here is we are trying to figure out a way where I can use a linear regression model when I know that the linear regression predictions can range from minus infinity to plus infinity. How do I I reconcile that with the fact that I need a variable that can give me only 0, 1 values, between values between 0 and 1. What I do instead is I take the log odds ratio. So I say I'm now going to take my dependent variable and I'm going to represent it in the form of log odds. The log odds can take values from minus infinity to plus infinity, even though the value, the variable that we are using is a probability. So remember, we are still using the p value, the probability value. Probability values are restricted to from 0 to 1. However, if I take the odds ratio, then they become from 0 to infinity. If I take the log of this, then I am allowing values of minus infinity to plus infinity. So this is how I sort of reconcile the linear regression model with a binary outcome. Now, what is an odds ratio? Actually, an odds ratio is a fairly standard statistical term used extensively in probability. It shows the probability of success relative to the probability of failure. So, if you're interested in horse racing sometimes or betting, you will get odds. Bookies will offer you odds. So, for example, if supposing the likelihood of success for a particular event is 0.75, then the odds ratio that you're going to be conveyed is 3:1. Right, 3:1. In other words, there is a 3:1 chance of success. Out of 4 chances, 3 times there is a success, you might win, and once you might lose. So, if probability of success is 50%, what is the odds ratio? The odds ratio is 1. There is an equal chance of 1:1 chance, right? The success and failure have equal chances. So, the odds ratio is actually not a vague concept. It is quite extensively used in probability and simply shows the likelihood of success versus the likelihood of failure. Now, if I take the odds ratio, then essentially what I have, an additive model if I want to do, I simply say log of p over 1 minus p, which is my y variable, equals to beta 0 plus beta 1 times my independent variable. So, beta 1 times x1, beta 2 times x2, etc. Now, if I didn't want it in the log form, then I could simply get a multiplicative model. I would simply say p over 1 minus p then becomes e raised to the power beta 0 times e raised to the power beta 1 times credit history. So, how do I convert a log back to a straight term? I simply exponentiate it. So, if I do e raised to power log of p over 1 minus p equals to e raised to the power beta 0 times e raised to the power beta 1. Remember that when you're taking the exponent, the additive model will become multiplicative. So, if you want an additive model, use log of p over 1 minus p and you get an additive model. If you don't want a log term, then essentially your model reduces to p over 1 minus p equals to e to power beta 0 times e to power beta 1 times credit history. So, remember that the advantage of having a model form like this is that values of y are not restricted to between 0 and 1, and that the log transformation has a linear relationship with predictors. In other words, a unit change in x, which is my independent variable, will lead to a fixed percentage change in the log of y, not y, but in the log of y. This is a standard regression equation. A unit change in x will lead to a certain, a beta 1 change in y, but remember y is now in log form. So, it will lead to a percentage change, a fixed change in log of y. When you have a log linear model, you can express the change in y as a percentage. So, one of the properties of a log linear model is that a unit change in x1 will lead to a percentage change in y when you have a log linear model. A log linear model is when your y variable is logged but your x variable is not logged. If you had a log model, then a 1% change in x will lead to a beta 1% change in y. That's an outcome of a log model. In this example, we are using log linear. So, a single unit change in credit history will lead to a fixed percentage change, which is a beta 1% change in the log y. Now, if you are using a multiplicative model, in other words, you don't want change in terms of log, but you want change in terms of real terms, the y variable, then you can do that. A unit change in x or credit history will lead to a multiplicative e to the power beta change in y. Notice that this is a multiplicative model. So, a unit change in credit history will lead to a e to the power beta 1 times multiplicative change in y. And this multiplicative e to the power beta is also called an odds multiplier. Now, there is an approximation. We can say that for small values of coefficient beta, the percent change in y can be denoted as 100 times e to the power beta minus 1. But for now, let's not worry about this. We'll come back to model form and interpretation shortly. Now, you may want to say that I don't even want to model P over 1 minus P. How do I express it in terms of P? So if you wanted to model it in terms of P, then the mathematically you can get P as e to the power beta 0 plus beta 1 x1 plus beta 2 x2 etc. by 1 plus e to the power beta 0 plus beta 1. So I have this model P over 1 minus P equals to e to the power beta 0 into e to the power beta 1 etc. If I wanted to state this in terms of P and not 1 minus P, this is what it would reduce to. Right, where P is the probability of event, beta 0 is the intercept, x is the independent variables, and all the beta k's are the slope parameters or the coefficients. So there is no issue really. The model, you can still model P or the probability, but it's easier to model log of P over 1 minus P, because then that's a very straightforward linear regression model and it is something that we all understand. So that's why the logistic regression is shown in terms of log odds ratio. You're converting a multiplicative model into an additive model by taking the log of the odds ratio. Now that we've seen the model form of a logistic and why we take the log of the odds ratio, in the next section we'll talk about how we prepare data for a logistic regression, and we'll talk about the estimation techniques in a logistic regression. We don't use OLS, we use another estimation technique. So we will cover that in the next section.